Hello friends, welcome to SnR Academy, your online coaching portal for GATE and IES 2018. So today is our lecture 1 of communication systems. So all of you who have not watched the introductory lecture, you can go to our YouTube channel and watch the first lecture where I have told about the syllabus and the exam orientation of the subject. So today I will be starting with the basics of communication systems. So let's go and let's start the subject today. Friends, today, as I told you, today we will be starting with the basics. So the first thing that we will cover would be some trigonometric identities. Then we will move to some basic signal and system. And finally, we will see some modulation. Why do we need modulation in communications? So this would be our agenda for today. So friends, let's start with this trigonometric identities part. So friends, I've got here some trigonometric identities. I don't want to waste time in writing all this down. That's all. Most of you would be aware of these identities, but just because I'll be using them a lot in my subject, so let's just go over them. So these three are the basic sum and difference formula identities. So I think you'll be aware of these. Then moving ahead, we have these few double angle formulas, that is sin 2 theta and cos 2 theta formats. So cos 2 theta, you can use all these three formats as you wish. But how we would be using them? The most used identities would be this power reducing. So from the above formulas we can get this sin square u and cos square u things. So this is your basic sin square u, cos square u. How would we change them to cos 2u formats? We don't need this tan square u, so we can leave this for now. And then moving ahead, we have this sum to product formula identities, where we can have the product of sin terms, the difference of sin, or the product or the sum or difference of cos terms. So we'll be changing these sum products to sum formats to product format. So these identities, these two power reducing and sum to product formulas, these two would be very important and frequently used. Similarly, we have this product to sum formulas, where we are doing the reverse process. So we have product of sin, cos or sin cos terms, and we will be changing them to sum formats. So I would like that if you can just note them down somewhere, or if you already know, then no problem. But if you don't, then better you can just note them down somewhere and then learn those, because we don't want to waste time in mathematics later on. So yeah, this is the trigonometric identities part. Now just let's move to the signals and systems part. Signals and systems, as I told, it's a very basic subject for starting communication. So I will not tell you the complete detail of anything, but whatever part we will be using in communication systems, that I will go over. So we will start with some basic functions that we used in signals and systems. So first of all, let's go through the basic functions or basic signals. So the first one would be unit impulse, or as we denote it as del t. So now this signal del t, it is defined at time t is equals to 0. So if this is the time axis, this signal would be defined at time t is equals to 0 with the value the value of this signal is not known at this time, and I am writing 1 here. This 1 will denote that this signal has an area of 1. So if I ask you the value of this signal, you can't say the value is defined at t is equals to 0, but what is defined is the area of this signal. So if I take minus infinity to infinity del t dt, so this value would be 1. That is why we are calling it unit impulse, because it has a unit area. Yeah. So now the second signal, which is basically an extension of this. So second signal would be unit step function, or I will denote it as u of t. So this unit step signal, let's see the graph how it is defined. So same thing, this is my time axis and this is my t is equals to 0 point. So this unit step function is defined for all values greater than or equal to t equal to 0. So if I write the definition of this function, so this is basically ut equal to 0, t less than 0, and it is equal to 1. 1 because it is a unit step function. So 1 for t greater than equal to 0. This value would be 1. So if I write similarly a function as a into u of t, so it is a unit step function with a magnitude of a. Now the similar to unit step function, I'll just have a modification in this. So instead of a unit step function, let's take a pulse function, or just let's call it rectangular pulse. So this rectangular pulse, it is kind of a unit step function, but we will not define it for all values t greater than equal to 0. We will just have defined it for, let's say, we will take it from t is equals to 2 to t is equals to 5 seconds. So this is your rectangular pulse. So if I want to write this function in terms of unit step function, if this value is a, so I can write it as a, since it is starting at u of t equals to 2. So if I shift this unit impulse function to t is equals to 2, that is how the function would look like. So ut minus 2 is basically starting at t is equals to 2 and going to t is equals to infinite. But I want to stop this function again at t is equals to 5 seconds. So I'll subtract a unit impulse function from this, which is starting at t is equals to 5. So this becomes minus u of t minus 5. So u of t minus 5, it is a similar function starting at t is equals to 5 seconds. So if I subtract these two signals, I will get this rectangular pulse. Similar, we can also have a triangular pulse, which I think you can define in terms of slope. As we are defining this rectangular pulse in terms of a value, we can define the triangular pulse in terms of slope. So let's move to the next function, which is like very frequently used in communications, and we'll be calling it as sampling function. And similar to sampling function, just another definition we will also take, which we will call as sinc function. So sampling function, let's say sampling of t. Sampling of t would be defined as sin t by t. So the sinc function is just a modification of sampling function. It's just a multiplication factor of pi. So if I define sinc t, it is sin pi t by pi t. So basically, if I want to write sinc in terms of sampling function, I can write it as sampling of pi of t. So these two functions become sinc. So sinc and sampling, they can be always interchanged. you will see sampling function more used when you are studying signals and systems, but when we are studying communication systems, you will use the sync format more than sampling format. So I want to just sketch the graph of this sync function. So let's take our x and y axis. So it comes to the time axis. If I want to sketch this signal, we can see it is a sinusoidal function, but it will be a sinusoidally decaying function. So if this is I want to sketch this function, I will sketch this as a sinusoidally decaying function. So if you see t is equals to 0, you can apply the limit. So sin 0 by 0 format and get the value 1. So basically it would be kind of this kind of a function. On both sides. It will be an even function. So if I want to define these values, where this is cutting the 0 points, so we have to take what is sin t equal to 0. So when sin t becomes 0, so t is basically your t should be plus minus n pi. N should not be 0 because at 0 we are using the limits to find the value. So this value will become pi, 2 pi, 3 pi, these kind of values. Similarly, if you want to draw the sampling function, then these values will be pi t equal to plus minus n pi. The sync function, sorry. The sampling function would be at these values. So sync function, basically these pi values, this will change to t is equals to plus minus 1. This value would be minus 1. Similarly, this value would be 2. This value would be 3. Same here on the negative side. This is how we are defining the sampling and sync functions. So these are the basic functions that we are going to use. So let's just see them again. So these functions here, these functions are unit impulse, unit step, rectangular pulse. Similarly, we can define triangular pulse as well. And then the sampling function or the sync function. So don't get confused between sampling and sync formats. These are almost same things, just a multiplication factor of pi is different. So now let's move ahead and now let's move to the second part, which is Fourier transform. So as we know, in communication we will be dealing with the frequency domain more than the time domain. So Fourier transform becomes a necessary tool to understand that. Fourier transform, it gives your transformation from your time domain to the frequency domain. So it could be omega or f. So these definitions will basically slightly differ how you use it in omega domain or f domain, but the concept is same. So if I want to define Fourier transform, what is the formula for Fourier transform? So that becomes, if you have a signal ft, then to define the Fourier transform of it, f of omega, let's say that becomes minus infinity to infinity, your signal ft into e to the power minus j omega t dt. So this f of omega is called the Fourier transform of f of t. Similarly, if you want to divide it in a frequency f domain, then it's the same thing. Basically, you will just replace omega with 2 pi f. Because 2 pi ft dt. So this is the definition of Fourier transform. So similarly, we can also take inverse Fourier transform, that is from omega domain to t domain. So to define that, just to I have the formula for that. Ft is equals to, just apply the reverse thing. So if you are converting from omega domain, there is a factor of 1 by 2 pi here. So this becomes 1 by 2 pi f of t into e to the power minus, not minus, plus j omega t. So these ft or f omega, these become the Fourier transform pairs. Now there are some properties of Fourier transform which we have to use directly, which are more extensively covered in signals and systems. But let's see the properties which we will use in communication as well. So let's move to the properties of Fourier transform. The first property we will see is time shifting. Time shifting property states that if you have a function f of t whose Fourier transform is defined as f of omega, then Fourier transform of f t minus t naught would be defined as f of omega into e to the power minus j omega t naught. So you can see there is a additional multiplication factor of e to the power minus j omega t naught. Similarly, if you take this as f of t plus t naught, same multiplication factor with a different sign. So e to the power j omega t naught. So this is your time shifting property of Fourier transform. Similar to time shifting, we have a second concept which would be frequency shifting. Basically, instead of shifting in time domain, we want to shift in the frequency domain. So again, if there is a signal ft with Fourier transform f of omega, then if I take a signal ft e to the power j omega t naught, and let's just keep it as, because we are shifting in frequency domain, so it becomes j omega naught t. So this will become as f of omega minus omega naught. So it's just the reverse property that we saw above. So if you are shifting in time domain, you get a multiplication factor in frequency domain. If you are multiplying with an exponential function in this, or rather than imaginary exponential function e to the power j omega naught t, then you get a shifting in frequency domain. That is the frequency shifting property of Fourier transform. Now the next property is, we just saw time shifting property. Now let's see the time scaling property. So as you all know that your time and frequency, time period and frequency, they are inversely proportional. So if you increase the time period, you are going to get, if you are doing expansion in time domain, you are going to get a compression in frequency domain and vice versa. So if I have a signal f of t here, Fourier transform f of omega, so if I take signal which is scaled by a multiplication of factor a in time domain, so this becomes 1 by mod of a f of omega by a. So you can see, depending on this value of a, if this is greater than 1, then basically you are doing a compression in time domain. So this leads to a expansion in frequency domain. Similarly, if this a is less than 1, then you are doing expansion in time domain, and it will cause a compression in frequency domain with a magnitude change as well. Remember that there is a mod here. Okay, so now let's see, we just saw some basic signals. Now let's take the impulse function again and let's see its Fourier transform. The impulse function is a very basic function. If I want to have its Fourier transform, simply 1. Similarly, if I have, now let's say we want to find the Fourier transform of this one. So basically we want to find the Fourier transform of a constant value. It can be anything, in this case it's 1. So for that we use the property of Fourier transform, which is very important property, which is called duality. So let's see the duality property of Fourier transform. So what does duality property state? It basically says, let's take a function x of t with a Fourier transform x of omega. This basically says, if you know the Fourier transform of a function xt to be x of omega, then if you want to find the Fourier transform of a function x of t, so basically this is capital X. So if you are just transforming this variable omega to t here, so this becomes 2 pi x small x of minus omega. So it basically says that take this function here, the time domain function, change the variable to minus omega. So basically you are doing a time reversal here and multiply it with a factor of 2 pi. So this is in omega domain, but if you want to do this in f domain, let's see, the property becomes slightly different, because if xt has a Fourier transform x of f, so this function x of t would have a Fourier transform of x of minus f. Basically this is more easier in frequency domain, you don't need this multiplication factor. So this one we will be using more in communication, because we will be dealing in f domain more than omega domain. So now we wanted to find the Fourier transform of this constant value. So let's use the duality property here to find that. So because we know, let's take an example here. So because we know the Fourier transform of del of t to be 1, so we can say by the duality property that the Fourier transform of 1 would be del of minus f, using the f domain here. So, but we know that del function, it is defined at t is equals to 0 only, so it is an even function. So it does not matter if you take f or minus f. So del of minus f is same thing as del of f. So if I have any constant value, so if instead of 1 I have a, so I will get its Fourier transform as a into del of f. Now let's just use another property with this one. So I am saying there is a value a, and I am multiplying it with a factor of e to the power j 2 pi f naught t. So this is the frequency shifting property, as we know, we have studied above. So this becomes a del of f minus f naught. So this is getting shifted in frequency by a factor f naught. Similarly, now instead of this exponential function, I am taking a cos omega naught of t. Let me write it as in terms of f, a cos 2 pi f naught t. So this becomes now, as we know that cos omega naught, we can write it in exponential form also. So we'll write it as a cos can be written as e to the power j 2 pi f naught t plus e to the power minus j 2 pi f naught t by 2. So now if you see this cos function as sum of these two exponentials, you can easily write the Fourier transform of this. So let's just do it using the example we just saw above. So basically a by 2 becomes your constant now. We know that Fourier transform of e to the power j 2 pi f naught t would be del of f minus f naught, and the Fourier transform of e to the power minus j 2 pi f naught would be del of f plus f naught. So now this becomes the Fourier transform for function a cos 2 pi f naught t. Similarly, if I had sin 2 pi f naught t, so no difference, we will use the same thing, because we know that sine can be defined as the difference of those two exponentials. Instead of sum, we will take the difference here. So it becomes e to the power j 2 pi f naught t minus e to the power minus j 2 pi f naught t by 2j. So now the constant also changes, it becomes a by 2j, and this would be del of f minus f naught plus del of f plus, sorry, not plus here, should be minus. This is minus. So this is how we define the Fourier transform of sinusoidal functions. So both sine and cos are sinusoidal functions. So this property is very important in communication systems. Multiplication with cos or sine. So the multiplication with sinusoidal functions. This property in Fourier transform is very useful, and we will be calling it as modulation property. This is also a property which is used extensively in communication systems. So when we will go to AM, I will show you how this modulation property is actually helping. Actually today if we start modulation, I will just show you how this modulation is actually very important in communication, because communication is all about modulation and demodulation. Now moving ahead, and also so another basic function that we saw was the unit step function, that is u of t. So let's just define the Fourier transform for this as well. So before defining the Fourier transform of this, and also like to introduce to another function which is signum of t. Signum of t is again, you can define it as this one. So basically you have the time axis. So it will take a value plus 1 for t greater than 0 and a value minus 1 for t less than 0. So it is basically two unit step functions. One, you can see this is just a unit step function. So in the negative time axis also you are taking a unit step function but inverted in value. This is your signum function. So if I want to change signum functions to unit step function, what I can do is I'll just write it as, I can write this u of t as half plus half signum of t. So if you can see here, if I multiply with this half, this value becomes minus half and half, and then I am shifting it up by half. So this again comes to be the unit step function. This is how we are taking the unit step function in terms of signum function. And now you will see in signals and systems that this signum of t has a Fourier transform of 2 by j omega. This also will get by duality property. I'll use directly here and write this. So above we saw how to get the Fourier transform of a constant using the duality property, this one. So we are just using it as a into del of f. I can also write it in omega domain. So as you remember that in omega domain we saw that we had an extra multiplication factor of 2 pi. So in omega domain it would be written as 2 pi into a del of omega. So I'll use this property here and we are writing this Fourier transform for u of t. So this half is a constant value. So I can write the Fourier transform as half into 2 pi del of omega. So the a value, constant value is half here, plus half into 2 by j omega. So let's just cancel these 2's. So we'll get the Fourier transform for ut becomes pi del of omega plus 1 by j omega. This is the Fourier transform for u of t. Now another function that we will see a lot in communication, I'll just define it as a function which we'll be calling as gate pulse. Gate pulse is basically similar to a rectangular pulse that we saw before, not much difference there. So gate pulse, but I will define this gate pulse function to be symmetric about the origin. It's basically your rectangular pulse only, but how I am defining it as minus t by 2 to t by 2. So I am defining this function to be symmetric about the origin. Let's take this value to be, this is your function f of t. So this is what we get. So now let's try to find the Fourier transform for this. So let's use the basic definition of Fourier transform to find this. So we know f of omega is minus infinite to infinite f of t e to the power minus j omega t dt. So because this function is defined from minus t by 2 to t by 2 only, it becomes 0 elsewhere. The limit changes to minus t by 2 to t by 2. The value becomes 1 and e to the power minus j omega t dt. So if I integrate this, I get this 1 by j omega e to the power minus j omega t from minus t by 2 to t by 2. So this becomes as, take this minus sign inside and put the limits here. So it becomes e to the power j omega t by 2 minus e to the power minus j omega t by 2 on j omega. Now let's just use multiplication factor of 2 here. So 2 I will just multiply and divide by 2, and this omega I'll take outside. It becomes like this. So if you see this part, now this part is what we saw as sine function. So e to the power j omega t by 2 minus e to the power minus j omega t by 2 is nothing but sine omega t by 2. Okay, so now this becomes 2 by omega sine omega t by 2. So what I am trying to do here is, I will just write this as 1 upon omega by 2 sine omega t by 2, and I will multiply and divide with a t. So now if you see this part, this looks to be of the form sine t by t. This is what we saw as sampling of t function above. So this we will put as sampling function. So finally what the Fourier transform becomes is t sampling of omega t by 2. So this is what we get the Fourier transform for this gate pulse. It is defined from minus t by 2 to t by 2 with the value of 1. So this is a conventional method to just to get this, but we have a shortcut method for this also. So what is the shortcut method? Let's just see that shortcut method now. So how you can just get this Fourier transform directly by seeing this function? So what you can do, I'll just tell you how by seeing this function you can tell its Fourier transform. So just a minute. Yes. So again I am taking some gate pulse. I am taking this value to be minus t by 2 to t by 2, and I am taking this amplitude to be a here this time. How we can directly write the Fourier transform? We know that this is going to be a sampling function here, so I can directly write it will be a sampling function. So when you see a gate pulse, you know that it is going to be a sampling function, and omega is the variable here. So now how to get this t by 2? So basically if you see the width of this gate pulse, it is t. So you can directly write it as omega into width by 2. So if you do width by 2, you get t by 2 here. And what is the factor that you will get here? So here you will get the factor, it would be area. So if I take the area of this gate pulse, it would be a into t, area of this rectangle. So at sampling of omega t by 2 is what is the Fourier transform for this. So because we had the value 1 here, this was the Fourier transform for this. So using this shortcut you can directly get this Fourier transform. Similar to this, we can extend this shortcut to a triangular pulse as well. So let's say a symmetrical triangular pulse here, which is defined from any value minus t to t to any amplitude a. So how I will define Fourier transform for this? Same thing, I'll go the same way. It would be area here. The area of the triangle you can directly half a into 2t. So a into t again, the area you will get. Area into sampling square. This time instead of sampling you will get a sampling square function. And inside this sampling square function you will get width by 4. The factor of width by 4 this time. Instead of width by 2 it becomes width by 4. So for this gate pulse it would become area would be a into t. It becomes sampling square of omega into width by 4. So 2t is the total width here. Total width is now 2t. So it becomes omega d by 2. This is how you can directly write the Fourier transform for triangular pulse. So I'll also like to express this thing in terms of sinc function. So I can write it as sampling of 2 pi f t by 2. As I told that sinc t, sampling of pi t are the same thing. Using that only I can write, because this is sampling of pi ft, I can write it as at sinc ft. So basically I'll just repeat this step here again in terms of sinc function, because I'm going to use it more often than the sampling function. So if this width is minus tau by 2 to tau by 2 in time domain, this is the t-axis, its value is a. So its Fourier transform would be at sinc of ft, f tau. So you can directly remember this as a standard result. It is an important result. This thing. So directly remember this as Fourier transform for this pulse would be a tau sinc f tau. So now you can use the duality property here also. So instead of this thing being in time domain, so this is your time domain here. This was a Fourier transform, so this is your frequency domain. So if I bring this thing to time domain, so if I want to find the Fourier transform for sinc function, which is defined like this, which is basically your sinc function, which is defined like this. So if I have to find the Fourier transform for this sinc function, it will be simply, because we know the from duality property that if f(x of t) has a Fourier transform of x of f, just by changing the variable xt will have a Fourier transform of small x of minus f. And again, because this pulse is symmetrical, so if I take f or minus f, it doesn't matter. So this comes out to be a rectangular pulse or gate pulse in frequency domain. So this axis is your frequency axis. So these two properties, again, this is very important. So if you remember the above result, you can directly conclude this from duality. So these two results are kind of standard result for our communication systems, very frequently used. So better we just remember them as standard results directly. Now I think I have covered the signals and systems part here, whatever we need for communication systems. So if you want to see, you can just have an overview of what we saw. So basically, when we started Fourier transform, saw a few properties which are time shifting, frequency shifting, and then we saw time scaling as well. So time scaling, I can use this property if I want to define another result here. Let's say I want to define another property here, time reversal. No difference. Basically, the value of a that I am putting is -1. This becomes f of minus t. If I use the same property here, so and small a again becomes 1, so it doesn't matter. So f of omega by a, this becomes f of minus omega. So inversion in time domain is also giving you an inversion in frequency domain. So that is a time reversal property. You can conclude that from time scaling property itself. Then moving ahead, we saw the Fourier transform for impulse function, which is directly a standard result, which is given as 1. So to find the Fourier transform, we use this knowledge of impulse function, find the Fourier transform for this constant function using the duality property. So we saw the duality property in both omega domain and in f domain. You should be aware how to use it both in omega and f. So we use that property to find the Fourier transform for constant. We use the frequency shifting property to define Fourier transform for cos and sine functions, and we called it as modulation property of Fourier transform. Then we found the Fourier transform of the unit step function, and then we saw how we define a gate pulse. Gate pulse definition I gave you, and also derived the Fourier transform for this gate pulse, which we now know we can directly find through a shortcut, the gate pulse and triangular pulse. So we don't have to waste time on this, we can directly use this shortcut, find the Fourier transform for this gate pulse and triangular pulse. So we saw this Fourier transform for this gate pulse and also use the duality property to find the Fourier transform for sinc function. So this is the signals and system basics part that would be leading in communication systems. Also another thing that we would be using would be filters. Filters is again detailed, you can find in signals and system itself, the transfer function definition of filters and all. But I'll just classify filters here as three types which we'll be using here: the low pass filter, the high pass filter, and the band pass filter. So the low pass filter is basically a filter which passes the lower frequencies. So low pass filter, basically it will look like something like this. So this is your frequency axis. It passes only frequencies up to f0. And this is your ideal low pass filter. So it is basically passing the frequencies up to f0 with a gain of 1. So no attenuation or no amplification. And then it is suppressing the signals outside, the frequencies outside this range, and making them 0. So high pass filter is just the opposite. It will pass all your frequencies which are greater than f0. This is how your ideal high pass filter would look like. And then band pass filter. Band pass filter, we can pass a certain range of frequencies which we need. So this is passing some frequencies from say f1 to f2. This is your band pass filter. This is only the basic part that we need for filters in communication systems. So now I'll start with the subject. So the first thing, just a second. First thing that comes is, what is a communication system? So what is a communication system? Basically it's just a system which is the process by which you can transmit some information from a transmitter to a receiver or source to destination via some channel. So now I will classify this communication system as two types. First one would be wired, and second one would be wireless. So let's see the difference between them. So first let's see the wired system. Wired system. So wired, we are basically using wires to transmit our information. So you know, because we have to use wire, we cannot use it for very long distance communication. So this will be limited to some short distance or medium distance communication. For long distance, we will prefer wireless. So first of all, let me classify the types of signals that we are going to transmit using wired or wireless, whatever it is. So first one becomes the voice signal, then the audio signal. Voice and audio, those are different things. Then comes your video signal. So the frequency range for these is, voice signal ranges from 300 Hz to 3.5 kHz. Audio signal, as you all know, is 20 Hz to 20 kHz. Video signal has a wide bandwidth, so it is 0 to 4.5 MHz. These are the three types of signals that we like to transmit using our communication system. So now the wired system. So the wired system, how it works? So this side you will have a source. Now the source will send this information to some source transducer. Why the transducer is needed? Because the information that you are sending is a voice or audio or a video signal, but you want to convert it to an electrical signal or an optical signal. In case of optical fibers, when you are sending it through a wired channel. So this channel now is wired. So again at the receiver side, you will need a destination transducer that will do the reverse job. And then finally this information is passed on to the destination, but whatever the receiver, the information is reached to the receiver. So this is how your wired system works. Now coming to the wireless system, see the difference where it becomes different from the wired system. Wireless system, as I told, it can be used for long distance communication because there are no wires here. So you will need antennas to transmit your signal. So the difference in the block diagram, I'll just show you the block diagram. So basically source, then the transducer, the source transducer. But now there's another box here. That box is your modulator. Why we need this modulator? I'll just tell you in a minute. Modulator, this signal goes to the transmitting antenna and it is transmitted via wireless channel now. At the receiver side, this will be received by the receiving station. Then it will be demodulated by the demodulator. And then again the same thing. So this would be your receiving transducer. And then finally your destination or the receiver. So this is a block diagram for wireless system. Now this is the difference between wired and wireless system, modulation and demodulation. So that is what the communication system, the first few chapters will deal completely on this modulation, demodulation techniques. So the question arises, why do we need modulation or demodulation? So the question we need to answer now is, why modulation? So first of all, the very first thing that we need to know is we have to transmit this signal through an antenna, and we know that antenna height, it is dependent on the frequency or the wavelength of the signal we are going to transmit. So it is approximately lambda by 4. So if I want to write it in frequency terms, I will write it as C by lambda as C by F. So if you see, if you have the lower the frequency you are trying to transmit, the larger the antenna height you require. This is less, then this is more. So ideally, if I want to transmit a 0 Hz frequency through my antenna, I'll need an infinite height antenna, which is practically impossible to have. So that is where the modulation comes into picture. So what will modulation do? So modulation, now we can see modulation simply as it is shifting your frequency. So if I say I had a signal which I wanted to transmit, so this is a frequency axis, I wanted to transmit this signal through a wireless channel. So if I see that I have this 0 frequency component, the lowest frequency component in your spectrum of the signal you want to transmit will decide the antenna height. So this signal has 0 frequency component, so you cannot transmit it through a practical antenna. So you need modulation. So what will modulation do? You will pass it through a modulator. What will it do? It will basically shift this entire spectrum to some other higher frequency. So if I say, let's say it was 10 kilohertz. So now this is shifted to a very high frequency. Let's say this would be like around megahertz. So this becomes like 1 megahertz. So now the lowest frequency component which you will see here would be like 1 megahertz. 1 megahertz minus 10 kilohertz. This value is significantly larger to what value we had here. So now you can see, because this value, we have increased this f value to this range, we can easily transmit it through some antenna of some practical height. So that is what modulation is doing. It is allowing you to transmit the signal through antennas by shifting the spectrum of the original massive signal to some new frequency range. And the demodulation process would be just the reverse of this. So it will just recover your original massive signal by shifting it again to the original zero frequency component. Now the second need for, not exactly the need, but that is a benefit we get from modulation, is we can do multiplexing of signals when we are doing modulation. What is multiplexing? Multiplexing is you can transmit more than one signals using the same channel at the same time. So how can you do that? So if you want to transmit more than one signal at the same time, you have to ensure that they do not have the same frequency component, because if they have the same frequency component, then they are going to interfere with each other. So if I have these two signals, so I can see that they have some common frequency components in them. So if I just transmit it like this, they are definitely going to interfere and will not be recovered at the receiver side. So how is modulation going to help me? I am going to modulate each of these signals to a different frequency range. So if I am shifting this spectrum to say 1 megahertz frequency, I will shift it to some another frequency, say 2 megahertz, just an example. So basically now these signals do not have a common frequency component in them. So they will not interfere. You can transmit at them at the same time, it can be received and then demodulated again at the receiver side. So this is the benefit that you get from multiplexing, or the benefit you get from modulation. Now let's just see, let's take a signal which we want to transmit, which we have already discussed, which was our gate pulse. So let's say this is the signal I wanted to transmit. So basically, when I am trying to transmit this signal, I need to see its frequency components. So how can I get this frequency components of this signal? So I will use the Fourier Transform tool here. Fourier Transform, we already saw that the Fourier Transform for this gate pulse is A tau sinc of f tau. So if I draw this signal in frequency domain, so this is a sinc function, and these values are, null values are 1 by tau, 2 by tau, like this. This signal, it goes up to infinity and minus infinity. So now how do I define bandwidth? Another important term, bandwidth. So bandwidth is basically, if you want the definition of it, it is the difference of the highest frequency component and the lowest frequency component. This is the difference of this lowest frequency component on the positive axis. So I am just going to consider this part, and not this side. So if I see this signal, you can see the highest frequency component is infinite and the lowest frequency component is 0. So the bandwidth is infinite. So this signal, which I was defining as a gate pulse, has an infinite bandwidth. So that is a problem now, because infinite bandwidth you cannot transmit. So because the channel bandwidth for good transmission, you need channel bandwidth greater than the signal bandwidth. The signal bandwidth we saw, it is infinite. We cannot have a channel bandwidth infinite. So what channels we have? If you want to transmit it through a wired one, so what channels can we have? Wired channels could be your coaxial cable, it could be your parallel wire, or it could be your optical fiber. So we know this, you can just remember the range of these three types of channels, the wired channels. So this is your 0 to 600 megahertz. Parallel wire would be 0 to the least 0 to 200 kilohertz only. And optical fiber has the maximum bandwidth, that is why it is the fastest. It is tens of gigahertz. So you can go to from 0 to tens of gigahertz value. But we cannot get infinite bandwidth from any practical channel. So this is like, it is practically impossible to transmit this kind of a signal. So what we are going to do is, we are going to do a process which is called band limiting. So what is band limiting doing here? Band limiting would be limiting a infinite band signal to a finite band. So this is an infinite band signal because it has an infinite bandwidth. So if you want to limit this signal, how can we limit this? So if you have this signal, what I'll do is, as I know that you can see the most of the energy of this signal, is concentrated in this part. So if I see just this part, it will give me around 90 to 95% of energy of this signal, or 90 to 95% of information of this signal is stored just in this part. So if I put a low pass filter here, which will allow just these frequency components. So what I'll do, I'll put the low pass filter here. So the output of this low pass filter would be, it will just give me this part of the original message signal. Now I can see that I have this some definite value which is defined here. So I can see this is now the bandwidth of my new signal, which is finite. Now it can be transmitted through a wired channel. Still we cannot transmit it through a wireless channel because it has a zero frequency component. So the antenna height required would be infinite. So we'll need to modulate it before we are ready to transmit it through a wireless channel. This process is called band limiting, and how we are achieving it? By using a low pass filter of suitable cutoff frequency. So now because we have lost some information here, but because I am retaining 90 to 95% of the information of the signal, so the major portion of the information is still intact, and I can reconstruct the message signal using this information. Friends, this would be it for today. So we just give a recap of what we saw in modulation. So when we started modulation, we saw two types of communication systems, wired and wireless. The types of signals which we want to transmit. Then the block diagram for wired and wireless channels. And what was the difference between wired and wireless was modulators and demodulators. So we saw the need of modulation. We found out that antenna height is, to maintain a practical antenna height, we require modulation, and another thing we get out of modulation is multiplexing. Then we defined bandwidth, how to define a signal bandwidth. So channel bandwidth should be greater than equal to signal bandwidth. So to limit this infinite bandwidth signal, we saw how to use low pass filters to band limit it to a finite bandwidth. So this would be it for today, friends. So this is where we are going to end today. So just let me know, friends, if you like this lecture. You can give any kind of feedback. If you want me to go a bit faster or a bit slower, or you want me to cover topics in more details, I can do that. So your feedback is welcome, and please subscribe to our channel as you want to stay in touch with us. And soon I'll upload the lecture 2 as well, where we will continue from the modulation, and we will then move to types of modulation techniques, which would be your AM, DSB, SSB and USB. So let's see where we will finish the next time. But thanks, friends, for watching today, and please subscribe to our channel and like our FB page. Thank you, friends. Have a good day.